So what we're going to do is we're going to visit back with our friend equilibrium. And you can tell we're going to be talking about equilibrium today because there's a capital K, right? Here's the deal. You just took a quiz over titrations. Were there any capital K's on that quiz? Any equilibrium, acid, equilibrium, Ka, anything? No. So did you use an ice table on that quiz? No, you didn't, did you? You used the BCA table. So since we're going back to equilibrium, guess what we're about to have to use again? An ice table. And so if you're using anything with a capital K, for example, remember weak acids, you have to find, you have to use the Ka in an ice table to get the equilibrium concentration of the hydrogen, so you can do the pH. Do you remember doing that and you messing it up and the free response we did it right? Do you remember that happened? So you have to use the Ka, so that's how you know that you need to use an ice table. Why am I saying this? Well, because as you're taking a test, you have to know what kind of table do I need and what am I doing. So, I guess I'll get started then. So, if you check your formula sheet for KSP, it's not on there. Ha 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 ha. So this is something you just have to know. So what is KSP? KSP, K is equilibrium, and the S stands for solubility product. The equilibrium solubility product. Well, why is it a product? Well, if we look at any kind of salt or solute, we put these in water. If you recall, calcium carbonate is not soluble. Carbonates are typically not soluble, and neither is lead to chloride, because remember, small, medium, large with a halogen makes the solid. Remember, they make a precipitate. Am I ringing some bells here? Trying to get you ready for your huge final exam in 4 weeks. Okay, cool. But if you recall, we had said that these things are insoluble, and that's not. Everything is soluble to an extent. So they're insoluble, but they're actually a little soluble. So today we're mathematically going to represent how insoluble or soluble they are, and that's fun. But check it out. If I'm looking at this this hydrolysis, like basically if I put this in water, that's hydrolysis, or the dissociation of this ionic compound. Hydrolysis is the same. Basically, if you put something in water, that's hydrolysis, okay? If I put this into water, it's going to make calcium ions and carbonate ions. If I write the equilibrium equation, or the equilibrium expression for this, I'm going to leave out the salt, the solid ionic white powder that I got out of the box that I had to get out of the soup. I'm going to leave that out because it's a solid. So when we write the equilibrium expressions for the hydrolysis of an ionic compound, dissolving something in water, you're not going to have any reactants because they're solid. So the bottom of the fraction ain't there. You're not dividing by anything. So it's a equilibrium solubility product because you just multiply. You're multiplying what they break up into. And y'all know that it's products over reactants. That's not a problem, right? And so if we look at this, we're still going to have to make the coefficient be exponents. It's still the same. Everything's the same as you already know how to do equilibrium, as far as and to the extent of how you remember to do equilibrium. So that's your little introduction. So far, so good. Oh, we gonna have to. We do it every day.
Nice, easy, simple.
Yeah. Well, you're moving on to bigger and better things. I have a problem, and it's not I have a problem. The AP exam, your test, everything about this example one is not correct. And let me tell you why. On a conceptual level, it has some trueness to it. So let's talk about it. If I told you the KSP for calcium carbonate is 8.7 times 10 to the negative 9, little to the left, right? That means that the reactants, the calcium carbonate, is obviously favored, so it's not very soluble in water. And then this one is 10 to the negative 5th. So this one is a little more soluble because it's a little bit more towards the products. There's more to this. You have to do math. You can't look at a KSP and just know which one's soluble. You can kind of eyeball it, but that doesn't work, and you'll fail your test in the AP exam if you do this. So this is not enough, and this is wrong. And so we'll get into that. This is a good way to say, well, these are both pretty insoluble. They both have small KSPs, whatever.
But there's more to it, I promise, and I'm sure. I'm super sure. So anyway, what is solubility? So when we say something is soluble, obviously it's going to dissolve. And so are y'all familiar with the term saturated solution? Saturated solution is holding all the solute it possibly can without being able to dissolve anymore. So if I had a saturated solution of salt water, I wouldn't be able to add another grain of salt. It couldn't dissolve. Okay, right? So a saturated solution, or the solubility, here we go, is the maximum molar concentration of formula units that will dissolve at a given temperature. So for every 1 mole of lead 2 chloride that dissolves 1 mole of, we're going to have 1 mole of lead, right? This is where those show your work, how many do you have in there. 1 mole of lead for every 2 moles of chloride ions, right? And then you can kind of write that down. So let me take you back to this last slide real quick. What this means for us is a number, KSP 8.7 times 10 to the negative 9th, is equal to a number times another number. And this number for calcium right here would be the maximum number, or maximum concentration, it's brackets, right? The maximum concentration of calcium that it can hold and be saturated, times the maximum number of carbonate ions that it can hold at saturation. When I multiply those two numbers together, I get that. And those are pretty small concentrations, right? That would be like 10 to the negative 4th and 10 to the negative 4th or so. You follow what I'm saying? So that's a very small molarity that could actually be in the water and be dissolved. So that's why this number is small. How do you feel about that? So this KSP, this equilibrium solubility product, is for at equilibrium, the maximum number of ions expressed in molarity that a solution can actually have before a precipitate is formed, before I have a solid, before I have calcium carbonate instead of calcium and carbonate ions. Conceptually, are you hanging with me? Okay. All right, so what we're going to do, we're going to take this real easy and slow. The solubility product constant, so that's the KSP, for lead 2 fluoride is 3.6 times 10 to the negative 8. Write the balanced chemical equation for the and on the AP exam, they're going to say for the hydrolysis of lead 2 fluoride. Hydrolysis, that hydro means water, okay? So go ahead and see if you can swing number 1. Just see what you got. You can write, hopefully, and you can probably do B. So try A and B, lead 2 fluoride, and of course I'm going to do them. C is up to me. C is on my watch that I have to do that one. How's A going for you? All right, check your part A for you. Check yourself before you in fact wreck yourself. So, when you dissolve something in water, if you choose, which I would not recommend, if you choose to say, I'm going to throw this in water, guess what? You're going to have to write lead 2 fluoride plus water gives you fluoride and lead plus water. Because you better have it on both sides. But so don't write water. Don't do it. Because you know that's going to cancel because it's going to play the matching game and you pull those cards out. How do you feel about that? Alright, so let's make sure we got some things. This is a solid. These are aqueous. Did you make sure you put the charge on the ion? You're shaking your head like, yeah, I learned that the first day of this class. Ha, I just graded your quiz, y'all. A lot of y'all didn't put your charges on your ions. So, yeah, and then we have 2 fluorides. Make sure everything's balanced. You got the same on both sides. We brought the equilibrium expression, KSP, is equal to the products over the reactants. So I'm going to have lead, and then I'm going to have fluoride, and then I'm going to need to make sure I square fluoride. And I don't include the solid because we don't put solids in equilibrium expressions. And so that's going to be equal to 3.6 times 10 to the negative 8. Have I left any children behind yet? You feeling okay about this? It gets much worse. But are we still together at this point in our lives? 3.6 times 10 to the negative 8. So the last question was saying, find the maximum molar concentrations of the ions in solution and the molar solubility of the solution. All right, so let me take you through this. I'm going to go to the big white screen. And the question was saying the molar solubility, right? So let's just make our ice table. I'm going to tell you some stuff. All right, so I'm going to write my reaction because I don't have it anymore. Solids don't count. I start with none and none. How do you feel so far? You cool? So just like always, this is going to be plus X. Now listen, for KSP, they don't use S. They use S. And they'll give you values in S. The molar solubility is the S. It's just like X, but we're going to use S. Okay, so this is plus S. This is plus 2S. This is S, and this is 2S. All right, so far so good. And so that S, that letter S, is the molar solubility. I'm just going to go over here to get the number that they gave me. 3.6 times 10 to the negative 8. And it's asking me find the maximum molar concentrations of the ions in solution and the molar solubility. So on part C, when it says the molar solubility, that's the letter S. So check this out. KSP, which was 3.6 times 10 to the negative 8, is equal to, we had lead, and then we had fluoride squared, right? So that means that that's equal to S times 2S squared. Are you cool with taking the bottom row of an ice table and fill it into the equilibrium expression? I just did, right? So that's going to be, don't mess this up, S times 2S times 2S, right, 2S squared, which is 4S cubed. Now, to get the molar solubility, I'm going to solve for S. S is the molar solubility. These numbers, whatever they are, these are things in brackets. These are moles per liter. That's molar solubility. And that's equal to 3.6 times 10 to the negative 8. I'm going to divide both sides by 4. So I'm going to get S squared, or cubed, is equal to that. Then I'm going to take the cube root of both sides. And remember that taking the cube root is raising it to the 1/3 power. All right, so I'm going to, in my calculator, take 3.6. Yes.
Why is it hydroxide?
Because it's S. Okay, so I'm multiplying. So that gives me 1 times 2 times 2 is 4. And then, right, S times S times S is S cubed. Oh, yeah, you're trying to add. I got you. Anyway, so I get 9 times 10 to the negative 9th. And then I'm going to take the cube root of that, which is raising it to the 1/3 power. And I get S is equal to 0.0021. This is the molar solubility. S is the molar solubility. Do you remember a minute ago I was like, you can't just look at the KSP value to determine which one has the high solubility? This is what you have to solve for. You have to solve for S to see which one has the high solubility. This is the molar solubility. You have to solve for this to compare solubilities, okay? Anyway, the other part of the question on part C was said, find the maximum molar concentrations of the ion in solution at equilibrium. The maximum number here would be 0.0021. The maximum number of fluoride would be 0.0021 times 2. That's it. This ice table, the bottom row is your concentrations at equilibrium. And equilibrium for a solution is at saturation, where you have the maximum amount. So, the maximum concentration of lead is going to be S, which is 0.0021. And for fluoride, is 0.0042. Yes, and the reason I know it's molarity, here, there, that makes me feel better. There. The reason I know it's molarity is because all these were brackets. And so that S is moles per liter, and all these things in brackets are molarity or moles per liter. Thanks. Okay.
Too loud.
All right, how you feeling, you guys? So that's the easiest first example. Outside. Moves on anyway.
What's the matter with you? That's funny.
She'll get rid of it.
So again, S is the molar solubility, and then if you plug it back in, lead was equal to S, and then the maximum concentration of fluoride was 2 times that, because it's the bottom row of the equilibrium in the ice table. The bottom row that is equilibrium in the ice table. All right, and of course, if we were going to fill this back into the equilibrium expression, this would eventually get squared when we fill it back into there. But we're not filling it into the equilibrium expression. We were looking at that bottom row anyway. So again, saturation means that the solvent has dissolved the maximum amount of solute that it possibly can. And again, it's at equilibrium, it's saturated. So what does that mean? It means if you have a solid at equilibrium, the amount that's going into solution and coming out of solution is equal. We don't need to know about entropy yet, or Gibbs free energy. Okay, we'll catch y'all after Thanksgiving on that. There's more letters and more math. It's going to be fun. I can't wait. All right, so remember our friend Q? I remember Q because I remember you messing your test up. Let's talk about Q for a minute. I actually still have the key laying on my overhead thingy. Y'all remember that last question where y'all were like solving the theory of relativity, and all you had to do, this last test we just took out, went over it the other day. All you had to do, you were given stuff and you weren't at equilibrium, and you just had to fill it in to the equilibrium expression and then do a number line. Yeah, Courtney, what? You did that, didn't you? You made a number line, you did. Yeah, I was like, yes, you're still my favorite person right now. Everybody else like was doing ice tables and craziness. If you're not at equilibrium, you can't do an ice table because the bottom row is not equilibrium. So anyway, on a lot of these, they're going to be like, you throw some of this salt in the beaker and some of this salt in the beaker. Is it going to make a precipitate or not? Well, you're not at equilibrium, you have no idea. So you're going to have to get concentrations, and then you're going to have to fill it into the equilibrium expression, and notice it's Q equals. This was on your last test. I had to do it with gases. But it's better to not be at equilibrium. It's kind of easier. That's not good. All right, so is that ringing a bell with anybody? Remember doing that? Okay, and then if Q is less than K, then it's going to go that way on the number line, you know, all that. Okay, cool. So that's that right now. Okay. Going back to the PowerPoint. So I'm going to go ahead and write out that expression we're just using. So I guess we had lead to fluoride, and then we had, and that's a solid, okay, and then we had the lead, and that was aqueous, and then we had the fluoride, and it was aqueous. Okay, so check it out. If Q equals K, you're at equilibrium, which just means you're saturated. You have a saturated solution. If Q is greater than K, then a precipitate will form because it's going to go toward the solid side. Q is less than K. Q's over here and K's over here. then I'm not going to make a precipitate because the equilibrium is going to go towards the aqueous side. Conceptually, how you feeling? Pretty easy, right? The math that you have to do to get to this is insane. So let's go ahead and get started. The bottom line is if you don't understand the concept, you're going to do this much work and then you'll be like, what was I doing? So I want to make sure that we're good on that part. All right, so moving on. So find the KSP for a saturated solution of lead 2 chloride if the concentration, if it's saturated, it says it's saturated, if the concentration of chloride is found to be 0.0325 molar. That means in the bottom of the ice table, the value for chloride is 0.0325. Can you conceptually follow me there? If you can't follow me, this is what you do if you don't know how to do something. I do it every time because I don't know what to do a lot of times. When in doubt, mole it out. Is going to moles going to help me? Can I even go to moles? No. Put it on ice. I got a K. That sounds like a really good idea. So even if you're doing a problem, you have no idea what to do, let's just go ahead and we'll make an ice table. So we got lead 2 chloride. I probably could have used some of that, but my eraser doesn't work. So so I have lead 2 chloride, right? That's a solid, or 2, whatever you want. And I have lead, and then I have 2 chlorides. There, that's an S. That looks good. And so from that information they just gave me, at equilibrium, the molarity of chloride is, I got it right here. True story, as soon as I walked over my computer, it was like, we're taking a nap. So it was 0.0325 molar. So the bottom line of this is 0.0325 molar. And I know I start with none. And I know this is plus S. And I know this is plus 2S. Can I solve for S? Yeah. So S is going to be 0.0325 divided by 2, which is 0.01625. There's my ninja math skills for you. I don't know if you're impressed, probably not. So that is my molar solubility. If I was asked to compare solubility of lead 2 chloride to something else, that is what I would need to solve for, the S. All right, but anyway, since lead is just plus S, at equilibrium, the molar concentration, or at saturation, will be 0.01625. I don't know why that's so crooked. I'm sorry. Let's just pretend it's like right here. Okay, great. A little bothered by that. So the question was asking, find the KSP. Well, can I find the KSP? Do I have enough information? KSP is going to be equal to the lead plus the chloride, and the chloride squared. So now I'm just going to fill in these numbers. Multiplied. Sorry. So the chloride is going to get squared. I have to put it in here. So now I'm going to push buttons on my calculator, and then I'll get the KSP. Make sure you use parentheses. Parentheses, 0.0325 squared. Close it up. And I got KSP is equal to 1.72 times 10 to the negative fifth. And this is a pretty common kind of question. I guess I won't say the tricky part, but the tricky part is just being like, oh, what do I do, what do I do? And then you go to your ice table. If you start filling stuff in, usually it falls into place, okay? Try to do stuff in your head, don't write down units, things don't fall into place. Your grade just falls, okay? So the second part is kind of the fun thing. Let's read the second part together and read. Will a precipitate of lead chloride, lead 2 chloride form when 200 milliliters of
3.78 times 10 to the negative second. Who made that solution, by the way? Molar sodium chloride is mixed with 100 milliliters of 2.45 times 10 to the negative second molar lead to nitrate. Assume that the temperature of the resulting solution is the same. So the reason they told you about the temperature staying the same, that means the KSP stays the same. Okay? So that's great. Now, we got to think about what's actually happening here. Okay? I'm trying to use this lead to chloride. That KSP was what we just found, which I already forgot. 1.72 times 10 to the negative. Okay, so I'm using that same KSP. Now, that KSP, if you recall, was my lead times my chloride. I ran out of room, but my chloride squared. So I just basically need to put in some numbers. I'm going to put these numbers in here. And I can't make it K, it'll be Q. Q is equal to the lead times the chloride squared. And then if Q is bigger than K, it'll go toward the precipitate side. Q is less than K, I won't make a precipitate. Okay. So we got to get some molarities to put in here because it's not an equilibrium. I'm not about to make an ice table. I can't. It's not equilibrium. So anyway, I have sodium chloride. Is that sodium going to do anything? It's a spectator. Nope. So I'm not really worried about that. And then I have lead to nitrate. I'm not worried about the nitrate. But I can figure out the molarity of lead, and I can figure out the molarity of chloride. Then I can put them in here, and then I can compare Q versus K. Now, it's not even that simple. I can't even, if you're already pushing buttons in your calculator, you're already wrong. Let me tell you why. That molarity is cute. This molarity is cute. But this is 200 milliliters plus 100 milliliters. Can I use those molarities? Nope. So let's talk it through. What you're going to have to do is you're going to have to go to moles of chloride and moles of lead. And then you're going to have to divide by 300 milliliters, or 0.3 liters. That will tell you the molarity of those two elements. You follow me? Because we're making a new solution that has a bigger volume. When we get those concentrations, then we can fill it in. We can do that Q versus K. All right, and now this is why it was so important. I was really stressing, like, make sure you're writing your units down and your symbols and all that. So, you ready? Let's do it. Let's do these things. Oh. There were so many crazy numbers. I'm going to start with the sodium chloride, okay? I have 200 milliliters, and I got to go to moles. So I'm going to start with 0.200 liters of sodium chloride. And then the molarity of that solution was 3.78 times 10 to the negative second. I'm going to moles, right? Moles of sodium chloride. Write it out, and 1 liter of sodium chloride. Why does it matter that I'm writing it out? Well, you get lucky right here. If this had been magnesium chloride, it wouldn't be a 1-to-1 ratio. And y'all just saw how that plays out on your quiz. You saw how it goes when it's not 1-to-1. You have to show your work. Anyway, I'm going to go ahead and multiply that. I'm trying to get chloride ions. That's what goes in the KSP with the chloride. I'm trying to get chloride ions, okay? So 1 mole of sodium chloride is 1 mole of chloride. And if you skip this step, you'll get lucky on this one. But I don't like luck. I'd rather do my work. Anyway, push buttons in your calculator, and we're going to get the moles of chloride. 2 times 0.0030, it's 0.03. 0.0378. And that's moles of chloride. Now, those brackets for KSP are not moles. They are molarity. The volume of the solution is not 200. It's not 100. It's 300. You follow me? I'm going to divide that by 0.300 liters, which is the 300 milliliters. And when I do that, I get 0.0252 molar chloride ions in the new solution that I have made. Okay?
I'm not done. I'm not even close. So I'm going to do the same thing now for the lead. And I want you to do it. You can do that. Show all the little symbols, all the little names, the whole way through. And y'all know who I'm talking about when I say that. Looks at neighbor. I'm coming around. Are you doing this with me? I hope you are. You can't go to moles and molar, you have some problems.
Literally and figuratively.
And notice I did, again, take the time. It's not sodium chloride, it's chloride. That's what we're concerned with. Do the same thing on the lead. So, lead's charge is 2+, so be careful there. All right, so did you get 0.0817 molar lead 2? Okay, so what were we doing? I was like, what were we doing? What? So what we're going to do is we're going to go write that back in the KSP expression, but we cannot write KSP because it's not equilibrium, so we're going to write Q. So we're going to write Q is equal to the lead. Remember, it was 1 lead, and then we had 2 chlorides. So it's chloride squared. So now we're going to fill these in. The lead is 0.00817, and the chloride is 0.0252 squared. And that will equal Q. My board is crazy, but I'm happy it's working. So Q is equal to 5.18. My sigmas, I guess I can have 3. So 5.19 times 10 to the -6. Here's my number line. I'll make it bigger. Woo! There's my number line. So there's Q. And then K was like bigger. There's 0, okay? Just for you number people. K was it 10 to the -5th? I don't remember the numbers, but it doesn't really matter. Something to the -5th is smaller, right? So here's the whole idea. 10 to the -5th, and there's 0. Just so you see how numbers work. Q is less than K. So
That means that as the system reaches equilibrium, right, it will have to go toward the ion side. So no precipitate will form. That's a lot of work to get to that. So Q is less than K, so no precipitate forms. Did y'all get all that? Okay.
Whew, that was a lot of fun. I enjoyed that. And they filled everything in. They got the same thing we did. And it's no like, you know, Q is less than K. And in this situation, I mean, you're not gonna you would have to continue to add lead and chloride to get to saturation, but it's not like that's not the system. So really, I think it would be better. They're probably right to say since Q is less than say K, the solution is really unsaturated. So that's why no precipitate forms. It's not a reaction. Do you know what I'm saying? As far as like we're gonna keep adding it. So it's better to say it's unsaturated, not as we reach equilibrium, because we're not adding more of it. It's not like we got some more over here and we're going to keep adding. So no precipitate will form because the solution is unsaturated, and that is because Q is less than K. All right. So that's not all of it. It's most of it. I want y'all to, I'm going to take a little, not break. I want y'all to try to do number 2 real quick. I'm going to give you like 5, 6, 7 minutes to see how, make sure you get it, and then we'll come back and do this last little part, okay? So Victoria's out and Grace is out. Anybody else? Check attendance real quick. I'll hit pause too, I guess. When you're looking at stuff like this, it's just going to sound like a bunch of letters and stuff. XYZ zebras, giraffes, the park, the moon, question mark. And so it's better to kind of get in your head what exactly is going on. So what we're doing here is we have a beaker and we're slowly pouring into the beaker sodium hydroxide. So I'm putting in there sodium hydroxide, okay? Cool. Inside the beaker already is calcium nitrate and sodium nitrate. Let's talk about calcium nitrate and sodium nitrate. What's that nitrate going to be doing? Not a dang thing.
That's iron. That's iron. You say sodium. Hello. It makes mistakes.
Oh, I wrote it right. I said it wrong. Is that right?
Yes.
Everybody's an expert until you can't do it by yourself. Gotcha there. So really, what's happening here, I'm just going to make that whole thing go away. No, not the whole thing. For all intents and purposes, though, like I really got this going on. You feeling me there? And I'm really, that's going to be a spectator too. I'm putting hydroxide into a beaker that has iron and calcium. I don't know what that is. Whatever, I can't erase. Floating around. And this question is saying, which one is going to precipitate first? Is that iron 2 hydroxide or the calcium 2 hydroxide? So what we're going to do, and it gives me the molarities of these, so that's good. What we're going to do is we're going to write the KSPs for these, and we're going to write the equilibrium expressions, or the equilibrium solubility products, is what I should say. We're going to write those expressions, and all things considered, I'm pouring this hydroxide in there. I want to figure out which one is going to precipitate first. So that's kind of complicated. Let me just go to the blackboard and we'll make it okay. This is so much fun, I can't help but skip. So I have iron 2 hydroxide, right? And that's a solid. And then that's going to give me iron and 2 hydroxide. How you feel about that? Okay.
Good. I'm glad you're happy. KSP for this one, I got it over here. Secretly on my computer, I have the directions on how to do everything. That's not true. But I do have these numbers, so I'm just keep looking back and forth. Oh, so the KSP for this is 1.6 times 10 to the negative 14. And the KSP expression is just going to be iron and 2 hydroxides, which gives me hydroxide squared. Now, in the question, it gave me that the concentration of iron to nitrate was 0.25 molar. It already gave me the concentration, and like I didn't add two solutions together, so that's the concentration. I don't need to do anything as far as like going to moles and dividing by another volume that we had to do in the last one. So what I can do right now, what can I fill in? I can fill this in, and I can fill this in. And the way we're going to fill that iron in, if you look back at the problem, we have 0.25 molar, and I'm writing this out because it's not always 1-to-1. Hello, quiz from yesterday. And for this solution, it happens to be that 1 molar iron nitrate, iron 2 nitrate, is also 1 molar iron. And so my molarity of iron is 0.25 molar. So I can actually fill that in. Like I can fill in that iron, and I can fill in KSP. And guess what I can solve for? This right here, when I get this answer, that will be the maximum amount of hydroxide that this solution can hold before iron 2 hydroxide is made. So when I solve for hydroxide, I will be getting hydroxide concentration at saturation. And as soon as I have more than that, I'll be making this solid. Okay? Now I'm going to have to do all that over here for that other one. And then when I solve for the hydroxides on both, let's just give some, well, let's just go ahead and get the same thing going on over here. Can you do that by yourself? I'll do it up here. I'll give you a head start. This is some ninja level stuff, man. I'm not into this. Calcium hydroxide 8. What's it? Okay.
That was a joke. I didn't watch it. I was feeling really good about it too. So, did anybody go ahead and solve for hydroxide on both of these? Did y'all do that yet? You can punch buttons in your calculator and do this. Can't do that part. Nah, I don't know if I can help you anymore. We're gonna go. We're gonna go ahead and go for the day. So go ahead and solve for hydroxide on both of these. I feel like the one on the left hand side was. I don't know. I don't remember what I did earlier. I have a lot of it. I'm gonna use a different pen. This one is tag team. I don't trust y'all, to be honest with you. Okay. I don't trust myself. Oh my gosh. Alright, somebody just put down the sink. They're never getting called again. Did they smash yourself over?
No, it wasn't me. I promise it wasn't.
So anyway, over here, if I take 1.6 times 10 to the negative 14, and I divide it by 0.25, and then I take the square root of that answer, I get, I'm going to write this number out for dramatic purposes, okay? So I get
Oh.
Push your face. Push all of your faces. Okay, that is not the answer to my problem. Okay, for dramatic purposes, I'm going to write this number out, and it was 0.0000. That's 5. Is that 5? Yes. Okay, and then over here it was like 0.007 or something. What was it? Anybody got it? 0.0076. All right, now listen to me. The most hydroxide I can have in this solution before I make a precipitate is 0.00252 mole. Now I remember back, and this one is 0.0076. Do you get that that's a smaller number? So if we remember back to the beginning, we were pouring hydroxide into this beaker. Which one's going to have enough to make a precipitate first? How about that one? Because it only needs that much. You following me? If this had been 1 and this had been 11 million, then you'd be like, yeah, that one's going to get it up first. And that's really the ratio that we're at, okay? So the answer is iron 2 hydroxide, because only 0.00252 molar hydroxide is needed to form precipitate, whereas it will take 0.0076 molar concentration of hydroxide to make a precipitate. And so obviously the situation or that requirement for hydroxide will be met first, because that's a smaller amount of hydroxide. Can you kind of hang with me there? Okay, that's fun. I'm having the best time. I have the time of the good news is, that's as bad as it gets. The bad news is, I ain't going to walk you through with your little handheld every time, right? I mean, I will, but they're working out all this stuff. There was the maximum for the saturation for the hydroxide. That's how they did it. And then they did the same thing for the iron, and that's the numbers we got. And so hydroxide will reach that molarity before it reaches that one. Thus, the iron 2 hydroxide will precipitate first. All right, so common ion effect, you should already feel pretty good about this. Lead 2 chloride is already not really soluble. So if I add some sodium chloride to that, it will decrease the solubility even more. A common ion effect, the equilibrium shift back to the product side, reactant side. How you feeling? That should feel real good in your head right now. You good? All right.
Same thing with, oh, if I put silver chloride in here, you know, silver doesn't dissociate all the way, so the common ion effect won't be as strong because all the chlorides won't be dissociated. So that's all this is saying. All right. We don't have to do that. Fishing, who cares? Okay, and we're done. Cool. The bins. That's probably better than having to do this homework. I'm not going to lie to you. All right, so what you're going to do, I'm going to let you take the answer keys. And you can skip, I wrote it down. Of course, I can't find it now. You can skip 7, 10, and 17 through 19. 7, 10, and 17 through 19, okay? I'm going to do number 1 for you. Is this a good time, or do you want to? I'm going to talk you through number 1. I'm not going to do it all the way. But look, anytime they ask you which salt is more soluble, you cannot just look at the KSP. That is super duper 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 wrong. No. Anyway, so you have to solve for the S. The S is the molar solubility. Okay? So we already did VAF2. If you recall that the KSP was equal to 4S cubed, you have to solve for S now. You divide that by 4, and then you take the cubic root, which your S will be like, I don't know, it'd be like 10 to the negative 2. I mean, I'm estimating. This one, because it's 2 ions, it will be S squared. And so then you take the square root, and you're going to get like 10 to the negative 4. So as far as which one's more soluble, the one with the higher S. So the first one is more soluble. But I'm telling you, you cannot just look at that number. That is not right. You have to solve for S. I'm sure. All right, anyway. Moving on with my life. And there you go. So again, you're skipping 7, 10, and 17 through 19. This math, though, look, they don't use the ice table one time on here. You know better than that. You're better, and you are better than that. I believe. Oh, Lord help us. This looks like a lot of fun. I wish you well. All right, so you can skip these last 3. Yay. Okay, bye.